we have seen Holden model or the Chern insulator, which is characterized by a non-zero Chern number, and the insulator is characterized by time reversal symmetry broken. There is no time reversal symmetry in the system, which is induced by the second neighbor complex hopping, which we have mentioned, and here's this picture of Holden. And later on in about 2004-2005, Kene-Mele, this is Charlie Kane and Eugene Mele, they have understood that it is possible to recover the time reversal invariance, and this would create another insulator which is called as a quantum spin Hall insulator. In fact, what they have realized was very profound, that if we include the spin degrees of freedom in the system, actual spin degrees of freedom, not the pseudo spinner that we have been talking about so far, then it is possible to regain back the lost time reversal symmetry. Of course, the system would not have a Chern number, or it will not be called as Chern insulator, but it will be another kind of insulator which is known as the quantum spin Hall insulator, which is what we will see. So, Kene-Mele, they proposed this model which is known as the Kene-Mele model, and these are the papers that you see that which were published in 2005 in the Physical Review Letters by both Kene-Mele. One of them is called as the quantum spin Hall effect in graphene, which they realized that because along with the spin orbit coupling term, there is the Hamiltonian respects all symmetries of that of graphene. So, it is quite likely that it will be there in graphene. And then they wrote another paper in the same year, or rather this paper came earlier than the next one, which says about a Z2 topological order and the quantum spin Hall effect. So, Z2 index or the Z2 topological invariant is the new topological invariant for this system, which is distinct from the Chern number, because in this system the Chern number is 0 because the system has time reversal invariance. Okay. So, this is what we are going to study, which goes by the name quantum spin Hall insulator. Okay. So, here of course, as I said earlier, that the time reversal invariance is not lost, it is in fact preserved in the systems, and the system will show protected boundary modes or edge modes, very similar to the Holden model or the Chern insulator, but here it will be spin resolved modes, and they are called as the helical edge modes that are present in the system. And as I said that they will be characterized by a Z2 invariant. So, let me write down these 2 points. So, helical edge states that are spin resolved and characterized by Z2 invariant, and we will see what the Z2 invariant is, and we will of course stick to a simpler situation in which the system has inversion symmetry, and there the calculation of the Z2 invariant is easier than of course without a translation, or rather the inversion symmetry in the problem. Okay. So, the main ingredient of this kind of quantum spin Hall insulator is what is known as the spin orbit coupling. Okay. And in the most simple way that one can understand is that the angular momentum and the spin are coupled, and if the scenario is like this, then we know that neither of L or S are good quantum numbers, and one actually talks about J, which is a good quantum number in this case, and one can find out the eigenvalue of this L dot S operator in the eigenbasis, which is spanned by J, J1, J2, M1, M2 and so on and so forth. Okay. So, the spin orbit coupling is as I said, it is an important ingredient in this problem, and This a special kind of spin orbit coupling is what we shall be talking about. It's called as a Rashba spin orbit coupling, and it has a special place in graphene because graphene is two dimensional, which has the inversion symmetry about the z axis is broken, and Rashba is a very possible candidate in graphene. So, we will be talking about that. And so, what kind of spin orbit coupling are we talking about here? We are talking about a spin orbit coupling. Let us write down a Hamiltonian, which looks like we may use a different notation, but right now we are using a lambda SO, which is nothing but that second neighbor hopping T2 that we have talked about in the Holden model. And then there is a sigma z, and then there is a tau z, and then there is a sz. Okay? And we will actually derive this term. A part of it is already derived, like this term is there in the Holden model. We just have gotten this sz extra. Now, this sigma z, just to remind you, is the sublattice degrees of freedom. Tau z is a Valley degree of freedom, and sz is the real spin. So, spin degree of freedom. So, sz equal to plus or minus 1 for a spin half particle. So, why this term respects time reversal symmetry? It respects time reversal symmetry because under time reversal symmetry, the tau z changes sign, that is one is taken from the k valley to the k prime valley, or k Dirac point to the k prime Dirac point. So, that changes sign. So, under time reversal, this tau z goes to minus tau z, and we will see in a while that sz also goes to minus sz. So, an upspin goes to downspin, and sigma z does not change sign because that is the sublattice degree of freedom, and under time reversal it does not change sign. So, there is no net. Let me also write that sigma z does not change sign. So, there is no net sign change, and this is the main thing about this quantum spin Hall insulators, and we now have taken into account the real spin degrees of freedom. Okay. So, if you take this sz equal to 1 and minus 1 separately, so plus 1 and sz equal to minus 1. So, this is one copy of the Holden model, and this belongs to another copy of the Holden model, okay, such that the Chern number or the Hall conductivity will be plus E square by h and minus E square by h, that is equal to 0. But nevertheless, one has a quantity called as the spin current, which is defined as Js, which is equal to h over 2e j up minus j down. So, this will be non-zero, and we will have a sigma xy, a spin Hall, let us write it with a s, this is equal to a non-zero E over 2 pi. So, it is a distinct topological insulator. Compared to Holden model. And 2D electron gas, we have used this abbreviation several times in presence of an external magnetic field. Okay. So, this is the new thing that is going to come, and it is a new form of topological insulator, the second kind, so to say, after the ones that we have seen for either 2D electron gas in an external field or a Halden model where time reversal symmetry is broken by a second neighbor complex hopping. Okay. So, in order to understand this better, let me talk about the time reversal symmetry in a spinful model. Okay. I mean, spinful model means a Hamiltonian that includes spin, real spin, or let me write it as in presence of spin. Let me remind you that the time reversal symmetry operator without any spin present in the problem is the complex conjugation operator. So, without spin we will write for this time reversal symmetry or symmetric system as TRS. So, without spin TRS operator is simply K, which is the complex conjugation. Okay. So, we can write it with a slightly tilted T, which is nothing but equal to K. But with spin, this is not sufficient. And let me tell you that why it is not sufficient. Okay. And the reason that it is not sufficient is that because this complex conjugation operator will act on the sigma x, let me write it with just K acting on sigma x will give sigma x, it will not change its sign. K acting on sigma y will give you a minus sigma y because sigma y is complex, and K acting on sigma z will give you a sigma z without changing its sign. But why do we want it to change sign? So, let us go back to that the spin orbit coupling and which is written as L dot S. Now, under this time reversal, L goes to minus L and S goes to minus S, so that there is no change in sign. Now, you see that since we are talking about spin half particles, we have resorted to the Pauli matrices. Now, you see that both sigma x and sigma z do not change sign, but we want them to change sign. So, there is some other operator that we need to think about, which will give us a change in sign for all of sigma x, sigma y and sigma z. And that can be done in the following sense. I am drawing a coordinate axis, but this is in the spin space. So, this is say x, this is y and this is z. So, this is actually Sx, Sy and Sz if you like, and then if I do a rotation by pi about the y axis, then x become minus x and z becomes minus z. So, rotation by pi x becomes minus x and z becomes minus z and y remains as y, because it is a rotation about the y axis. Now, this is, as I said, that this is in the spin space, which means that such a rotation will make sigma x to minus sigma x and sigma z to minus sigma z, and will not do anything to sigma y, but sigma y by virtue of being complex will change the sign under the these complex conjugation. So, we are looking for an operator that does this rotation about the y axis by pi. And if you remember the quantum mechanics, angular momentum of quantum mechanics, such a rotation is written as so this rotation operator is written as exponential, say for example a minus I pi Sy by H cross. Okay. And now the time reversal operator will be this into K. Okay. And since we are talking about this Pauli matrices or rather spin half objects, we can make a simplification that Sy is equal to H cross by 2 sigma y, and or rather all components will follow this relation, that is Sx equal to H cross by 2 sigma x and Sz equal to H cross by 2 sigma z. So, if we do that, then this complex conjugation operator will be like exponential minus I pi by 2 sigma y. Okay. And then of course, we will have to write down this. So, let me deal with this for the moment, and this is easy to work out. So, this will we can write this as a cosine of pi by 2 sigma y and a minus I sine pi by 2 sigma y. So, let me show how this simplification is done. So, cosine pi by 2 sigma y is equal to, so cosine of pi by 2 sigma y is equal to 1 and minus these pi by 2 sigma y whole square. There is a half factor here, which is 1 by 2 factorial, and then there is a 1 by 4 factorial and pi by 2 sigma y to the power 4 and so on. So, there is a plus minus. Now, this can be written as if you remember the properties of the Pauli matrix, then this sigma y square equal to 1, and that gives you that sigma y cube is equal to sigma y and so on and so forth. Okay. So, each even power of sigma y will give us 1 and each odd power will give us just simply sigma y. Okay. So, that tells you that this becomes equal to 1 minus there is a 1 by 2 factorial, and then there is a pi by 2 and so on and so forth square plus 1 by 4. So, it is a pi by 2 whole to the power 4 and so on, and this is nothing but cosine of pi by 2, which is equal to 0. Okay. And similarly, but the sine of pi by 2 sigma y will have these all the odd terms which are there. So, this is equal to a pi by 2 sigma y minus 1 by 2 factorial pi by 2 sigma y cube and a plus 1 by not this 3 factorial, I am sorry, this 5 factorial pi by 2 sigma y whole to the power 5 and so on. Okay. So, this is nothing but equal to, so because your sigma y cube is sigma y and there are sigma y. So, that is sigma y into a sigma sine pi by 2 sigma y, which gives you, so this operator is exponential minus I pi by 2 sigma y is nothing but minus I, the sine pi by 2 equal to 1. So, it is minus I sigma y, and that tells you that this time reversal operator for a spinful case, which is what we wanted to derive, is nothing but a minus sigma y and a k. Okay. So, that complex conjugation will be there. So, this is quite known. So, that is the operator there and so on. Now, what do we do with this, in the sense that how is it useful and what are the consequences of time reversal symmetry in a spinful model? And a priori the consequences are quite significant. It gives you what is called as a Cramer's degeneracy. Okay. So, let us see what Cramer's degeneracy is. Okay. All right. So, now we have of course written down that this is equal to a minus I sigma y k if you take a square of that, then it is equal to minus I square and sigma y square equal to 1 and k square of course equal to 1 as well, because you do twice complex conjugation it comes back. So, this is equal to minus 1. Now, there is something very important, that in a spinless system where there is no spin, tau square equal to 1, or these time reversal t square equal to 1 for a spinless system. Now, this minus 1 actually has a lot of interesting thing to go along with, and let me see that and how does it lead to the degeneracy. What happens is that suppose if psi is an eigenfunction of a Hamiltonian with energy E. Well, this Hamiltonian is TRS invariant, that is time reversal symmetry invariant with energy E, then T psi is also another eigenfunction, or rather T psi is actually perpendicular to or orthogonal to this. It is also another eigenfunction with the same energy. And this degeneracy is called as a Kramer's degeneracy. So, how do we see that this T psi is and what is the nature of T psi? T psi is perpendicular or orthogonal to this. So, you take a inner product of psi and T psi. So, this is just the T is written with a slight bit of curvature. If I forget that, you carry on with your notation. So, this is equal to a T square psi because so T psi, okay, T square psi because T you do this time reversal twice and should come back to the psi, and so this is nothing but a minus psi because T square is equal to minus psi and T psi, and this is equal to minus of psi and T psi. And now this cannot be possible unless psi and T psi is equal to 0, because if you take this the last term on this side, then it becomes twice of this, and then so that means that I mean 2 cannot be 0. So, this psi and T psi are orthogonal. Okay. So, this is one of the important implication of the time reversal symmetry in a spinful system, that they are orthogonal to each other, but they have the same energy, and this is called as Kramer's degeneracy. So, this is Kramer's and these psi and T psi are called as Kramer's doublets. All right. So, let me come back to this band theory that is block states. So, let us talk about the block states which has k as a good quantum number. Of course, the system has crystalline symmetries and so on. So, if you consider a block state, which means that we are talking about a psi k with a spin sigma, this is equal to a exponential I k dot r and u k sigma, where sigma is a spin and sigma can be up or down. This is according to Bloch's theorem. So, this contains the periodicity of the potential, and there is a free wave or there is a plane wave term there. Now, if I operate this psi k sigma, then what happens is that, so I will have to operate it by I sigma y k on this exponential ik dot r uk sigma, and so this k will act on this and will make this exponential minus ikr the plane wave part, and we can write this as so exponential minus I k dot r, and then we have of course a minus I sigma y u k sigma, and now you see that this can be written as exponential of I minus k dot r, and then the job of this I sigma y will be to invert the spin. So, if there is a sigma spin, then there will be a sigma bar spin, where sigma, if sigma is up, then the sigma bar will be down. Okay. And because this looks like a minus k, so this becomes equal to a minus k and a sigma bar, and the bar, so sigma equal to up, sigma bar equal to down, or vice versa. So, this is equal to exponential minus I k dot r and a u minus k sigma bar. Okay. So, that is what happens when you apply psi k sigma on this. So, which implies that there is of course a degeneracy such that E k up is equal to E minus k down, and this is called as a Kramer's degeneracy. Okay. So, there is a degeneracy of these up and down states for one given value of k, but if it is plus k for the up spin, then it is minus k for the down spin, or vice versa. And this of course has we know that this has a lot of implications on the topological insulators. So, what it means is the following, that let me show this just a picture. So, we will sort of see it like this. There is a so, I am just drawing parabolic bands for up and down spins. They could be, I mean, you can interchange them, does not matter. So, this is E as a function of k, and you see that at k equal to 0 they sort of touch each other, but the degeneracy is here. So, there is these 2 points, let me use a color to mark them. So, this point and these points are degenerate, but they correspond to 2 diametrically opposite points in the Brillouin zone, and that is where the degeneracy comes. So, for up spin it is at a k, well, we have done it just the other way around. Let me change the spin indices that way. So, this is down and this is up. So, this is that k. So, E at a k is degenerate with E at a minus k. E at k for an up spin is degenerate with E at a minus k for the down spin, and this gives the rigidity of the edge modes in this particular spin full system, or the Kene-Mele model that we are going to discuss in just a while. Okay. And so, the backscattering from a state, a k up state to a minus k down state are forbidden, and that is why these edge states are these are robust states. So, let me come to this model. The model is a very intuitive model, and which has been introduced by Kene-Mele, and that is their name that appears in the model and so on. This is the usual tight binding term that we all are familiar with, and we have been seeing this in the context of graphene several times. It is just Ci sigma Ci dagger Cj. We have not written any spin index here because it does not matter, it is a spin polarized term, which is just the tight binding kinetic energy of graphene. Now, this is what we have done. Just one small change that has occurred is that there is a sigma sigma prime term where sigma sigma prime can be up or down, and this lambda SO was nothing but T2 in the Holden model. So, Holden model is exactly the Holden term, but rather 2 copies of the Holden term, one corresponding to spin up with a flux which is given by pi by 2, and the down spin corresponds to a flux which has exactly equal and opposite magnitude, which is equal to minus pi by 2. And this is of course the term that we are familiar with, that is the inversion symmetry breaking term, the term that was there in graphene, because if we had sort of different chemical potentials at the 2 carbon atom sites, which are which are analogous to the hexagonal boron nitride. So, that is the term which is inversion symmetry breaking term. This term without the sigma sigma prime there, it would have been just the normal Holden model, but now you see that this part is taken into account, that is the spin Sz is taken into account, and they are taking sort of components of that, and this is of course the chirality. Okay. So, that tells you that if the second neighbor hopping is clockwise, then it has a positive sign, or if it is anti-clockwise, it has a negative sign, and this we have taken the flux to be exactly equal to pi by 2, and that is what is done, excepting when we wanted to generate the phase diagram, which is flux versus the this term. This term means with a lambda v term, which is the mass term that opens up a gap, inversion symmetry breaking term. So, it is basically 2 copies of the Holden model. Okay. So, this is Holden model with flux pi by 2 for the spin up, and for spin down it is minus pi by 2. So, this Kene-Mele term, so this is called as a Kene-Mele term. Okay. This Kene-Mele term is actually up Holden Hamiltonian for phi equal to pi by 2. Phi is the flux which is due to the So, this flux is exponential I phi. I mean, it is called as a Holden flux, but this is that term that comes with the T2 term. So, that if phi equal to pi by 2, then it becomes equal to IT2 and so on, IT2 or minus IT2. So, in the absence of any Rashba kind of spin orbit coupling term, the Kene-Mele Hamiltonian looks like the H up and H down and so on. So, it obeys time reversal symmetry. How that is not difficult to understand, we have done that here. So, this was the term. So, lambda SO sigma z and tau z and Sz. So, this was there in the Holden model. So, this was Holden term which was time reversal symmetry broken term, and this Sz has returned or recovered the time reversal symmetry. So, now what can happen is that one can also add a term which is called as a Rashba term. We will sort of detail about this later. The Rashba term is written as I lambda r, and then there is a Ci dagger, and then there is a sigma cross d vector. So, this d vector is basically some vector. It just looks like a vector kind of coupling, but then you see that we have taken a z component, and of course, that there is a lambda v term, etc. So, what one can get is that now with this term there, one actually gets the spin filtered edge states in the problem. Okay. So, which means that at each edge you will have a up and a down, the spin states or edge modes corresponding to up and down. So, at each edge there are 2 spins, up spin and down spin, and so on. So, these are called as the helical edge states. Okay. So, quantum spin Hall effect can be observed in the system, and the system will show a quantum spin Hall conductance of E over 2 pi, but will have 0 charge Hall conductance for the reason that we have already said. For having a Hall conductivity, you need to have the time reversal symmetry broken for the charge Hall, the usual Hall effect that we talk about. So, this is the full tight binding Kene-Mele Hamiltonian in the momentum space. These are the diagonal term, which are something like second neighbor hopping or on-site potential, and these are the kinetic energy, nearest neighbor kinetic energy terms and so on. So, each one of the terms are written carefully here. There is a full tight binding model. So, this tight binding model has term, this one in the low energy limit this Hamiltonian looks like, other than so there is only the Kene-Mele term that looks like this lambda SO, sigma Z, tau Z and SZ. Okay. And this is what we have discussed. If you do all these expansion, then this is of course the kinetic energy term or rather the near tight binding, nearest neighbor tight binding term and so on, and these are the term which is coming from the Kene-Mele term. So, this is the Kene-Mele term and this is the Rashba term. Okay. And this Rashba term does not do anything to the time reversal symmetry. Heuristic argument has been already put forward there, that is when you have a L dot S kind of coupling, both L and S change their signs and one does not have any net sign emerging out of that. So, this is a time reversal invariant Hamiltonian, and this Hamiltonian now had to be, we will sort of discuss about a little more about the Hamiltonian, but before that let me show you the calculation of the Z2 invariant. So, given that it is a 4 by 4 Hamiltonian, in the K space it can easily be diagonalized in order to calculate the eigenvalues and the eigenvectors. And once when we get the eigenvalues and the eigenvectors, we know that we can calculate the topological invariant. And let us just think that let us take two occupied band corresponding to two spins which are psi I and psi j. These are the occupied band wave functions, and the overlap of the time reverse block states are calculated using this formula. Okay. What is important is that one has to calculate this thing which is nothing but minus I sigma y k, which is what we have shown, and they have to be calculated between the two occupied band wave function. And what turns out that there is some epsilon function and then the Pfaffian of which is a function of k. Now, this Pfaffian, I will just come in a moment what is a Pfaffian, but this Pfaffian is 0 at k and k prime points, and while at the 4 symmetry points that is these k and the k prime points, this Pfaffian is equal to 0 once one calculates this matrix element. This matrix element will come in the form of this will have numbers and so on, and these numbers for a 2 by 2 will give me a Pfaffian there. And so, this is it's 0 at the k and the k prime points. In fact, if you calculate it over this entire rhombus, which is that red triangle plus the black triangle, then the Pfaffian would come out to 0 and the topological invariant will not be there. Okay. But if you calculate it only over half the triangle which is denoted by red, which are the C1, C2, C3, then it has a value equal to +1. So, it is actually defined as the Z2 is defined as 1 by 2 pi I, and these closed contour integral over this red curve C, that is C1 plus C2 plus C3, and it is a dk dot the gradient of the log of this quantity. This is just taken for convergence by Kene-Mele, but one can actually put that equal to 0, it still works. So, it is a log of the Pfaffian that is important. Now, what is Pfaffian? So, if you take a 2 by 2 Hamiltonian, Pfaffian is just the that off diagonal element. Okay. So, this is the off diagonal element, and for a 3 by 3 Hamiltonian, if you have such a matrix structure, then the Pfaffian is 0, and for a 4 by 4 matrix with the diagonal elements to be equal to 0. So, this is actually a purely off diagonal matrix, all the diagonal elements are strictly equal to 0. So, this is equal to A into F minus B into E plus C into D and so on. So, but of course, we are interested in only these Pfaffian which is of a 2 by 2 matrix. So, we need to do this integral, and this integral needs to be, so this is a C1 fx kx ky dkx and fy dkx ky dky and so on, and then over this C2, so this C1 and then C2 and then C3. So, this along C1 and then C2 and along C3 the same kind of integrals that will be there. Now, I am just showing you integral 1, that is I1, and for I1 you can't do this integral simply because there is a kx and ky dependency, and these integrand of course is a function of kx and ky. So, along C1 and C2 it is slightly non-trivial because of this kx and ky dependencies, but along C3 of course your kx is constant and it is only ky that changes. So, if you take C1 and the equation of this line that goes through this point gamma through M1, it is nothing but ky equal to kx by root 3. So, in this integrand, that is I1 integrand, we have fx which is a function of kx and ky. So, this is actually kx and kx by root 3, and the integral has to be done. This has been found out carefully, that this is that gamma point is 0 0, and the x coordinate of this point here, that is, let us call it as O A B and so on. So, it is a O A B O integral. So, this integral is that you see here is over this O A B O. Okay. So, that is the thing that needs to be substituted here, and then this integral is from 0 to 6 pi by 3 root 3. This has been found as 6 pi by 3 root 3 and so on. And if we substitute kx equal to root 3 ky, that is what the equation tells you, then this becomes equal to root 3 ky and ky over dky, and ky goes from 0 to 2 pi over 3 and so on. So, these are the double integral is calculated in 2 steps. So, this is step number 1, in which first you do the kx integral and then you do the ky integral. Okay. And similarly, one has to do the C2 over I2, and for I3 only dky is non-zero because kx is constant. So, kx is fixed at a value 0. So, we need to only calculate this. So, now you calculate over this C1 contour, and this is that C2 contour, and this is that C3 contour, and then you add integral over C1 plus C2 plus C3, and that should give you a topological invariant. Okay. And this is exactly the plot that one gets from this. You see that there is a dark blue line which is like a contour of this enclosed region, and this blue line, the dark blue line, that represents a gap closing scenario for this Kene-Mele model, which means that there is everywhere on that plot or on that line contour, the gap is equal to 0 at the Dirac points. Okay. And the gap is non-zero only inside in the sky blue regime. Okay. This sky blue place, or this inside, this is the Z2 invariant calculated using the formula that we had given above. So, this is equal to 1 and it vanishes outside. So, Z2 is equal to 0 here and Z2 equal to 1 here, and there is a blue line that separates. So, the topological phase transition occurs from the invariant being 1 inside or in the enclosed region, and it is 0 outside in the outside region. Okay. So, how do we know that it is a topological or it has edge states? It is not a normal insulator, and we do the same thing that we have done earlier. We take a zigzag edge ribbon or ribbon with a zigzag edge, and well, one can do also an armchair, which is a little different, and I believe that one had to or one has to take a larger system. But now you write down the Hamiltonian according to the hopping, all the hoppings that we have between red to blue and red to red and blue to blue and so on and so forth. Okay? And if you want more details on this, there is a very recent paper 2023 who have calculated, there is an explicit derivation of the helical edge modes for the Kene-Mele model. And so there is elaborate paper that one can actually look at. We have calculated the same things. Now you see that we see the spin filtered edge modes. So the spin filtered edge modes of the Kene-Mele insulator are shown for two different values of lambda v. So lambda v equal to some value and lambda v equal to some other value, which are taken as 0.1 t and 0.4 t. Remember that 0.1 in unit of t means the unit of the nearest neighbor hopping, and that's a little larger value. And just to wanted to make sure that 1 corresponds to the topological phase, this is the topological and this is the trivial. Because you see there are edge modes coming out from the conduction to the valence band, and they are cutting the Fermi energy at these green dots, the points that you see there, which are named as PQRS. So all these PQRS are here. So at one edge we have P and S, the other edge we have Q and R, and of course there is no edge modes here. So there is a bulk gap. So this acts like a band insulator. The figure on your right is a band insulator, and the figure on your left is a topological insulator. So this is chosen because we have chosen plot that is here, that is inside this sky blue region. So inside the sky blue region we make sure that it's a topological insulator with spin filtered edge modes, and the topological invariant is equal to 1, while on the right figure, which corresponds to lambda v equal to 0.4 t, which we have taken this thing equal to 0. So the lambda v equal to 0.4 is somewhere here and so on, and of course your lambda r values such that it's z2 equal to 0. So in the z2 equal to 0 case, we do not have any spin filtered edge modes. And just to remind you that in this situation, we have taken the kx to be a good quantum number and ky is not a good quantum number. So the Hamiltonian is written in the y direction, is written in the real space. So the size of the Hamiltonian depends on how many unit cells we take in the y direction. And in the x direction, of course, it's an infinite. So this is called as a semi-infinite nano ribbon, which is what we have talked about earlier. And we see these edge modes, and these edge modes are cartoon of that has been shown earlier here, that you see that these are the edge modes, these red and the light green, they correspond to downspin and upspin respectively at each of the edges, and that's exactly similar to what we get here, you see. So these correspond to the P correspond to the down, so P corresponds to up, S corresponds to down, Q corresponds to down, and R corresponds to up. Okay. So this is exactly the picture that we have shown. It's been reproduced using numerical simulations by us. So this, to summarize, this represents a completely new kind of topological insulator, which is marked by a new or a different topological invariant. It has time reversal symmetry. The states have Kramer's degeneracy. So these Kramer's degeneracy is what we are talking about. We have talked about that there are up and down states which are degenerate. So these up and down states at the k values, you see that that there are these P and S are degenerate states at but they are differ by a momenta which is on diametrically opposite parts of the Brillouin zone. I mean, they differ by the momentum there and so on, and then you also have these other set of things which differ by these momenta across the Brillouin zone. Okay. So this is a different kind of scenario where spin orbit coupling plays an important role. We have talked about two kinds of spin orbit coupling. One is a Halden term with a spin term added to it, or rather it is a spinful Halden term, which is also sometimes called as a intrinsic spin orbit coupling, and the Rashba spin orbit coupling has been added. Both respect time reversal symmetry. System has time reversal symmetry, and there are, instead of chiral modes, there are spin filtered edge modes which are there present in the system. So, we have been able to show another topological insulator or topological insulating state, which is different than the ones that we have seen earlier, either in the context of 2D electron gas in a magnetic field or the Halden model. I will stop here. Thank you.